So here we're trying to find the sum of all possible integers a such that there exists an integer n that satisfies the equation a factorial times 2 to the floor of square root of a equals n factorial. And we can like cancel a little bit. So we get, this becomes 2 times the square root of a equals n times n minus 1 all the way over to a plus 1. And immediately this is a problem. Because if we have more than 2 terms over here, if we have at least 2 terms over here, or if like even if we have like n times n minus 1 on this side, one of n and n minus 1 is going to be odd and the other is going to be even, which means that this right hand side can't be a power of 2. This right hand side cannot be a power of 2 unless a plus 1 equals n. Because like 5 times 4, n times n minus 1, in general, and like n times n minus 1 will never be a power of 2. It'll have like odd factors, so it can't be a power of 2. And so this means that actually 2 to the floor of square root of a is going to have to equal n, which will also equal a plus 1. And so now we found our construction for n. At this point, we're just trying to find a such that 2 to the floor of the square root of a is equal to a plus 1. And at this point, there is unfortunately no nice solution to this, really. No like a really easy way to deal with this. The best way to deal with this is to just say, wow, this is going to get really big. That's the best way to deal with it. It's going to just say it's going to get very big. And so let's just list out the small values of a, and at a certain point, the left side will just start getting too big, and we'll know it'll never, right-hand side will never catch up because the right-hand side is linear, left-hand side is exponential. So we just start writing out values. A equals 1. So when a equals 1, I'm going to swap it actually. So a equals 1. And we're going to choose a such that a plus 1 is a power of 2. So let's set up a table. When a equals 1, a plus 1 equals 2, and 2 to the floor of square root of a is also 2 to the first. When a equals 2, 3 is 4, 2 to the first. A is equal to 7, 8, 2 squared. A equals 8, not 8, I need to stop doing that. A equals 15, 16, 2 cubed. A equals 31, 32, 2 to the fifth. A equals 63, 64, 2 to the 7th. A equals 127, 128, and 2 to the 11th. And at this one, we can notice that the right-hand side is absolutely massive. That's 2,000, and the 128 is a lot less than 2,000. The right-hand side is only going to ever get bigger. And so at this point, we know that it's not going to work out. You could technically prove this more rigorously by like actually bounding it, but that's by like bounding it with induction. Because at this point, going from like 127 to 255 doubles here, but over here it's going to more than double. But yeah, you can just say the right hand side. This is not a proof problem. So at this point, it's not going to work. And so we're just going to go back and check, oh, line up here and we line up here. And so our solutions are going to be a equals 1 and 31. And so the sum of these two is 32. And so yeah, That's the answer to this one. A equals 1 and 31 are the only values that work. Main idea was that it has to be 2 to the floor. The main idea is that n has to equal a plus 1. And that's the only n that'll work.